again, welcome to the next part. Now we want to discuss the topic open fissure structure. We already discussed the normal simple structural or open structure of normal simple open structure of your glucose. So let's consider the open fissure structure. Fissure structure means we have to represent the molecule in a vertical pattern with cross links or cross lines. Where the cross lines are represents the number of chiral carbons. So what about the glucose? We know the structure of glucose, that is CHO, CHOH, 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 and finally a CH2OH, right? So actually, how much asymmetric carbons are there means, how much chiral carbons are there means, these all four are chiral carbons. These four are chiral carbon, ready? So let me convert this in open fissure structure. Convert this into the open fissure structure. Okay, this is open normal structure. Convert this into open fissure structure. So since there is four chiral carbon, four asymmetric carbon, we have to represent four junctions like this. Okay, where the top is an aldehyde carbon CHO and the bottom one is CH2OH. Ready? Okay. Right side. Now let's configure this chiral carbon, or let's arrange the valencies of the horizontal valencies of this chiral carbons, where all valency have H and OH. Okay. So what about the structure means? So you have to by heart the order of your stereo arrangement of glucose. In the second carbon, this is second one, third one, fourth one, fifth one, right? This is the first carbon, this is sixth carbon, as per the IUPAC priority. In the second carbon, the OH will be on the right side. In the third carbon, H on the right side. Okay. Fourth carbon, OH on the right side. Fifth carbon, OH on the right side. This is order. Second one, OH right. Third one, H right. Fourth one, OH right. Fifth one, also OH right. If OH is right, then the left will be H, right? If H is on the right, left will be OH. OH on the right, left will be H. OH on the right, left will be H. This is the open fissure structure of glucose. Okay. So we have more than one chiral carbon here. Okay. So in fissure projection, usually if you have a function group here and hydrogen on the left side, and this is a chiral carbon, this is a chiral carbon. Okay. Then if hydrogen on the left side, then that conformer or that configuration is said to be D configuration. That configuration is said to be D configuration. If you are taking the mirror projection of this molecule, it will be like this, where the hydrogen on the right side. If hydrogen on the right side, then it is said to be L configuration. If hydrogen on the left side, it is said to be D configuration. If there is one chiral carbon. If there is more than one chiral carbons are there, then consider the lowest chiral carbon. Lowest chiral carbon means a chiral carbon with the least priority. Okay. And check the position of hydrogen on that lowest chiral carbon. If it is on left side, then it is said to be D form. If it is on right side, then it is said to be L form. So now your glucose have number of chiral carbon 1, 2, 3, 4. Fine. But simply consider. So if more than one chiral carbon, you have to consider the lowest asymmetric carbon. Lowest asymmetric carbon is the lowest chiral carbon is the fifth chiral carbon, right? So the fifth chiral carbon, what is the speciality? In fifth chiral carbon, your hydrogen is on what? Your hydrogen is on left side. So this is said to be glucose, not a simple glucose. This is D-glucose. This is the D-glucose. Okay. So the molecule is D-glucose. Ready? So you can imagine how it become a L-glucose. 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 You simply take the mirror projection of this one, then the H will be on the right side. So then that is said to be L-glucose. L-glucose. Okay. But the naturally occurring glucose is D-glucose. D-glucose is naturally occurring one. Ready? Fine. And you know, if molecule is asymmetric, I think you are familiar with this formula in your optical isomerism. If molecule is asymmetric, which means the molecule have no symmetry, and N be the chiral carbons, the molecule is asymmetric, and N be the chiral carbons, fine. then number of optical isomer is equal to 2 raised to n. Number of optical isomer is equal to 2 raised to n. Ready? 2 raised to n. Ready? So if you are applying this formula, number of optical isomer in glucose. Both the chiral center is 4, right? 1, 2, 3, 4. 4 chiral centers are there. So number of optical isomers in glucose is equal to 2 raised to 4. And the 2 raised to 4, the answer will be 16. And the 16s are said to be, and the 16 isomers are said to be epimers. They are together known as epimers. Epimers. Okay. 16 isomers are called epimers. Ready? Epimers. Can you identify that 16 isomers? We know the form. This is an aldohexose, right? Yeah. We already discussed about the aldohexose. Okay. Actually, there are 8 aldohexoses are there. Glucose, glucose, allose, artrose, mannose, idose, talose, etc. Galactose, etc. There are 8 glucose, glucose, galactose, allose, artrose, idose, mannose, talose. 8 isomers are there, right? 8 isomers are there. And there will be 8 D-glucose, right? And the 8 D-glucose with a 8s are D configuration, and there is a mirror image also with a L configuration. So totally 16 isomers are there. Ready? And the most important among these 16 are glucose, galactose, mannose. Among these epimers, the most important are glucose, galactose, and mannose. Glucose, galactose, and mannose. Okay, fine. What is the relation between glucose and galactose? Galactose is C4 epimer of glucose. C4 epimer of glucose means 4th carbon rotated by 180 degree. 4th carbon rotated by 180 degree. Listen. Let's consider what is glucose. This is glucose. First carbon OH on the right side. Second carbon OH on the right side. Third carbon H on the right side. Fourth carbon usually OH on the right side. But here for making galactose, okay, fine. Let me draw the normal glucose. Okay, and here it is OH. Here it's CH2OH. Here it is H, OH, H, right? And this is normally the glucose. Okay, you simply turn the C4th carbon in 180 degree. Then you obtain the galactose. So which means galactose will be like this. Here is the OH. Here is the H. This is galactose. Okay, galactose. Then what about mannose? Mannose is a C2 epimer. Mannose is a C2 epimer of what? Glucose. Mannose is a C2 epimer of glucose. Okay. So let's check how a C2 epimer can form. C2 epimer. C2 epimer. Wait. Mannose is a C2 epimer of galactose. C2 epimer of galactose. Okay. I'm sorry, it's not galactose. It is glucose. C2 epimer of glucose. Okay. Which means second carbon rotated by 180 degree. And this is a structure called D-galactose. This is actually D-galactose because the lowest asymmetric carbon where the H is on the left side. Okay. And let me draw the D-mannose. Okay. In as usual style, CH2OH. Here is the CHO. And this is second carbon. Where the second carbon usually OH on the right side. Here H on the right side. Third always H on the right side. Fourth always OH on the right side. Fifth also OH on the right side. So this particular structure is said to be D-mannose. D-mannose. See the change. The change is in the second carbon. Here the change is in the fourth carbon. Okay. Fine. So that's all about the open structure, open fissure structure also. Now moving to the cyclic structure. Okay, there are certain limitations or there are certain reactions of glucose which is not able to explain by the open structure. Let's discuss that points. And then we can conclude that there is a cyclic structure for glucose. Okay, and we can move to the cyclic structure of that glucose. Ready? Listen here. Okay, limitation of open structure. Limitation of open structure. Okay, write down. The open structure of glucose is not able to explain. The open structure of glucose is not able to explain the following reactions. The following reactions. Number one, no pink color with the Ship's reagent. Actually, usually the aldehydes can show a pink color with the Ship's reagent, but here Ship's reagent is not forming a pink color with the glucose. Even glucose is an aldehyde. Okay, so no pink color with the Ship's reagent. Number two, no addition reaction with the sodium bisulfite, NHSO3. Usually aldehydes can form crystalline bisulfite addition precipitate with the sodium bisulfite, but your glucose is not able to show that reaction. Next, no orange precipitate with the 2,4-DNP. You know that every carbonyl compounds can show 2,4-DNP test. Every carbonyl, whether it is aldehyde or ketone, they can form 2,4-DNP test with the 2,4-dinitrophenylhydrazine. But here, now our glucose is not able to show that. Okay, next. The next is glucose pentacetate do not form oxide. Glucose pentacetate do not form oxide. Glucose can form the oxide. We discussed that in the last part. But glucose pentacetate is not able to form the oxide. Glucose pentacetate not form oxide. Okay? Ready. Number 5. It exists in two crystalline forms. It exists in two crystalline forms. Actually, glucose experimentally observed that the glucose exists in two crystalline forms. So all these different types of explanations indicates that there is no free aldehyde group. There is no free aldehyde group in glucose. Okay. Actually, the aldehyde group of glucose is not much free. Ready? So let's consider the aldehyde group. Let's consider the freedom of the aldehyde group. Okay. So by checking the molecular structure, it is clear that, or it is observed that it have a cyclic structure. Glucose have a cyclic structure. And in that cyclic structure of glucose is actually it is a hemiacetal. It is actually a, what is cyclic structure of glucose? It is a hemiacetal. Hemiacetal formed by the addition. What kind of addition? It is a hemiacetal formed by the addition between OH of C5, OH from the fifth carbon with a CHO, aldehyde group of first carbon. Okay, I think you are familiar with the hemiacetal formation. If you have an aldehyde like this, ready, which on reaction with the alcohol, which on addition with an alcohol, you obtain hemiacetal, right? Or simply H placed to the, you can place the H to the oxygen, carbonyl oxygen, and R to the carbon. Ready? And what is the addition product between an aldehyde group with an alcohol? That is said to be hemiacetal. Ready? So this is a hemiacetal structure. This is said to be hemiacetal. Okay. So like this, there is a hemiacetal form in the cyclic structure of glucose. Okay. Or in the open structure of glucose, so that there forms a cyclic structure. That is actually the introduction to the cyclic structure. So let me draw the cyclic structure through a hemiacetal formation. Listen here carefully. Okay. Let this be the glucose. This be the glucose, which means the open structure of glucose. Let me show the carbonyl group. Okay. And here is the OH. Here is the H. And the fourth one is also OH. Fine. Here H. Here OH. Here H. What about the fifth one? Fifth one also have OH. Fine, no problem. Now our discussion is that there is a hemiacetal formed between the OH. There is an addition of OH to the CHO from C5 to C1. Okay, so this is the C1, right? And this is a C5. Agreed. So there is an addition, hemiacetal formation between the OH and CHO of C5 and C1. So this H is added to, when the alcohol is added to aldehyde, H is added to the oxide and O carbon added to the carbon, right? So H is just to the oxide and the remaining part forms a bond with the carbon. Ready? And we obtain structure something like this. Now the chirality of, now the first carbon become a chiral carbon, right? Okay. Because all for different valence, all valency will be different, right? And there is a cyclic formation there is a bond formation between the fifth carbon oxygen of carbon with the first one. Okay. So let me discuss or let me draw this structure carefully. Listen carefully. Actually, there is initially there is 4 chiral carbon, right? But now there is 5 chiral carbon because the first carbon also a chiral one. Ready? Now, this O become what? OH. And there is a bond from the fifth carbon oxygen from the fifth carbon to the first carbon and H on the right side. So let me show that. So there is a bond connecting oxygen to the fifth carbon. That's perfect. Now that's perfect. And let this be the first carbon, H on the left side and OH on the right side. Ready? So this is the first one. And the rest is same. What about the second one? OH on the right side. What about the third one? H on the right side. What about the fourth one? OH on the right side. What about the fifth one? That is connected to the top. Okay. Now the bottom one is CH2OH. And this is H. And this also H. But here is the OH. Here is the H. Ready? Now this becomes the cyclic structure of glucose, right? Yes. Right, in the first carbon, right OH, second right OH, third right H, fourth right OH, fifth one connected to the first one, and then there is a top, on the bottom side, there is a CH2OH, okay? And this is a cyclic structure, what we called as alpha D glucose. What is? This is simply a D glucose. What is this one? This, we already know that this open fissure is a D glucose. But when there forms a cyclic structure something like this, then that is said to be alpha D glucose. Alpha D glucose. And there is one more possibility. Okay. This is actually a planar carbon. Okay. Ready? So the addition turns to the molecule into tetrahedral, right? sp3 carbon. So there is no need to arrange the OH on the right side and H on the left side. There is one more arrangement is possible since it is a tetrahedral one. That is, listen here. One more arrangement possible means let this be the first carbon which is connected to the fifth one. Okay. And the bottom there is CH2OH. Clear? Fine. Here is H. Here is OH. Here is H. And this is the fifth one, fourth one. This is the third one. Third one H. OH. Second one OH here. H here. What about the first one? The first one have a possibility. In the previous one, the first one, the OH is on the right side and H is on the left side. And this first carbon, due to the addition, it may be arranged on the right side, OH may be arranged on the right side or on the left side. There are two possibilities actually. Okay. We can't predict whether this is a possibility. So we have to consider the whole possibility. So there are actually two possibilities. Due to this two possibility, the first possibility OH on the right side, the second possibility H on the right side. Ready? See the difference. See the difference between these two. And this difference makes two crystalline forming glucose, such as alpha D glucose and beta D glucose. So this is said to be alpha D glucose and beta D glucose. Clear? Alpha D glucose and beta D glucose. Ready? So this is the difference between alpha D glucose and beta D glucose. Okay. So go through the concept clearly. Ready? So let me define or let me discuss the next structure, that is said to be Haworth structure. Before that, What is the difference between alpha D glucose and beta D glucose? Put it as a not point. The difference between alpha D glucose and beta D glucose only on the configuration of C1, right? Alpha D glucose and beta D glucose differ only in configuration of what? Configuration of what? C1. Called, and they are collectively called, alpha D glucose and beta D glucose are collectively called anomers. Anomers. Okay, anomers. And C1 of glucose, where there is the difference, or where that carbon brings the difference between alpha D and beta D. Okay, so that C1 of glucose called anomeric carbon of glucose. C1 of that glucose called anomeric carbon of glucose, because that brings the difference between anomers. Okay, anomeric carbon of glucose. So now consider the Haworth structure. How much chiral carbons are there in alpha D glucose and beta D glucose? Actually, 1, 2, 3, 4, 5. 5 chiral carbons are there. Okay. Oh, dark. Wait. So let's consider the Haworth structure. Okay. Write the heading Haworth structure. Here the Haworth structure is actually based on what? Haworth structure is actually based on the comparison of glucose. Glucose is compared with the comparison of glucose with the pyran. Okay, comparison of glucose with the molecule pyran. What is the molecule pyran? The molecule pyran is something like this. This is a molecule pyran. Okay, fine. Pyran means having 5 carbons on the ring and 1 oxygen, which is connected with the oxygen. This is a molecule. And we know the alpha D glucose. Okay, so I have the alpha D glucose. Your alpha D glucose is something like this. This is connected to the first one, right? Yeah. Here is the hydrogen, here is the OH, here is the H, here is the OH, here is the OH, since it is an alpha D glucose, H, OH, H. So this is alpha D glucose. Okay. So how we can draw the structure of alpha D glucose? In comparison with the pyran means, you can draw the structure like this. This is actually pyran. 1, 2, 3, 4, 5. 5 carbons connected by oxygen. There is no need of multiple bond, okay? And all carbons having 2 more additional valency, or 2 valencies on the ring side, and 2 more additional valency, and this valencies represents the chiral centers. This is a chiral center, chiral center, chiral center, chiral center, chiral center. Okay, this is most convenient represents the reactions of glucose. So we prefer the structure Haworth structure. Okay, and you simply turn the molecule into reason. Now here the numbering is 1, 2, 3, 4, 5. Okay, and here is 1, 2, 3, 4, 5. So in order to design the valencies, of each carbon, this numbered in clockwise direction. Right? This is numbered in clockwise direction. So turn the molecule into clockwise, or you consider the valencies on the clockwise direction. This is numbered in clockwise direction. So simply turn the molecule into clockwise, so that the right valencies on the bottom side, right? Valencies arranged on the right side will be on the bottom side. So you place that valencies on the bottom side. Okay. So which means Valencies which are corresponds to right side on the bottom side if the direction of numbering is clockwise. Valencies which are corresponds to the right side will be on the bottom side if the numbering is in clockwise. So first carbon OH on the bottom side because that's alpha D glucose. First carbon OH on the right side. Second carbon always OH on the right side. Third carbon always H on the right side. Fourth carbon always OH on the right side. Fine. And corresponding valency here will be H, here will be H, here will be the OH, here will be the H. And now listen one more. Now we want to sort this carbon. This carbon, one valence is connected to the oxygen which is connected to the ring. Fine. This carbon, one valence is connected to oxygen, oxygen is connected to the ring. That's okay. So now you want to show these two. Ready? So these two we can arrange. If you are drawing the D-glucose, D-glucose, always CH2OH on the top side. If you are drawing the D-glucose, always CH2OH on the top side. That's the rule. Okay. For D-glucose, CH2OH always on the top side. So this is the alpha D-glucose in clockwise direction. Alpha D-glucose. And alpha D-glucose which is drawn in Haworth structure or in comparison with the pyrene structure. If your glucose is compared with the pyrene structure, then it is said to be glucopyranose. Structure of glucose on comparison with the pyrene said to be glucopyranose. So this is actually alpha D glucopyranose. This is actually alpha D glucopyranose. Alpha D glucopyranose. This is simply alpha D glucose. This is alpha D glucose. And its Haworth compared with the pyrene said to be alpha D glucopyranose. What about the alternate structure of alpha D glucose? We can draw the molecule in this pattern also. Something like this. We can number this in counterclockwise direction, which means anti-clockwise direction. Okay. So for design the valencies in the anti-clockwise direction, you simply tilt the molecule in anti-clockwise. So left side on the bottom side, left valence is on the bottom side. So the first carbon, left valence is H. Second carbon also H. Third carbon, the left valence is OH. Fourth carbon, the left valence is H. Okay. And always CH2OH on the top side since that is a D-glucose. And H on the bottom side. Ready? Fine. And the corresponding valency here is OH. Here is OH. Here is H. Here is OH. Ready? And this is also alpha D glucopyranose. Alpha D glucopyranose. So I think you are okay with the alpha D glucopyranose. We are usually using this structure in clockwise direction always. Okay. This is also acceptable. Ready? Okay. So just see this structure. Now need to study the corresponding order. And this is you have to study in by heart pattern. Okay. Because we are using this structure usually. Ready? And let me draw the molecule. This is alpha D glucose. Fine. We already write this here, right? So how this can be turned to a beta D glucose? This is the anomeric. You have the anomeric carbon. You simply tilt the valences of anomeric carbon so that the first carbon hydrogen on the right side, that is said to be beta D glucose. So what will be the change in Haworth? In Haworth, the first carbon, if hydrogen on the right side and you are numbering this in clockwise direction, then the right side valence become on the bottom side. So it will be H on the bottom side, OH on the top side. Like that, if it is in counterclockwise direction, what happened? Left side valency on the bottom side. So left side valency here is OH, OH on the bottom side, H on the top side. Okay. So this how your molecule turns to what? Beta D glucose. Sorry, beta D glucopyranose. So both alpha D glucopyranose and beta D glucopyranose are anomers. Still now that is anomers. Okay. And the number of chiral carbons in alpha D glucose, alpha D glucopyranose, D glucose, etc. In cyclic structure actually there is 5 chiral carbons, and open structure actually 4 chiral carbon. Okay. So not that point, not number of chiral center. Number of chiral center. In D-glucose means, simply D-glucose means that's an open structure. So N equal to 4. In alpha D-glucose means alpha D or beta D-glucose. It means a cyclic structure. So N equal to 5. In beta D-glucopyranose means connected with the pyran, that's an average structure. Okay. Here also, this is also a cyclic structure. So N equal to 5. Keep it in mind. Okay. So in cyclic structure, always the number of chiral carbon in glucose is 5. And in open structure, it is 4. Clear? So that's all about the structure of glucose. Now we want to discuss the next fructose. Before that, there are some properties for your alpha D glucose and beta D glucose. Let's discuss that.